Remember, when we start talking about waves, one of the important properties of a wave, the frequency, we said it is determined by the source of the wave, the frequency and the original amplitude. Now, we also noticed that whenever a wave moves from one medium to another, the frequency does not change. Okay, we notice that the wavelength and the speed change, but the frequency does not change. The only time that we can see a change in the frequency after it is being produced is what's called an apparent change through what we call the Doppler effect. This apparent change happens whenever the source of the wave that's producing the wave at this frequency, and the observer, the detector of that wave, it can be a human ear or a microphone or whatever, are in motion relative to each other. Now, whenever observer and source move relative to each other, we are going to see an apparent change in the frequency. The frequency is going to appear higher when the source and the observer approach each other, and it's going to appear lower when they move apart from each other. Now let's explore this in more details. Okay, so here we have a source of a wave. The wave is not moving, but the observers are moving. One is approaching it and one is moving away from it. As the animation runs, you'll see the wave fronts as being produced. This number here represents the number of wave fronts that are produced by the source. This number represents the wave fronts detected by this observer. And this number, of course, is representing the wave fronts as detected by this observer. Okay, as you see the replay, this one, since he's moving closer to the source, he's seeing more fronts for the same amount of time. So he's going to see the waves to be more frequent, a higher frequency. However, for this one, since he's moving away, the wave fronts are not catching him as often, so he's seeing less waves than the waves being produced. Compare these two numbers. So he's going to perceive a lower frequency of the waves. So to summarize and put it formally, whenever the observer is moving towards the source, for example, if this is my source and the observer is moving towards it, so the velocity of the observer, v sub o, is negative. The time between wave peaks or wave fronts decreases and the frequency increases. However, whenever the observer is moving away from the source, this is not exactly the way we saw it in the simulation, but the same idea. So the observer velocity is positive, the time between wave fronts or wave peaks increases, as observed by the observer, so the frequency decreases. Formally, the expression giving us the frequency as perceived by the observer, f sub o, is equal to the frequency of the source, that's the original frequency, times 1 minus the velocity of the observer, whether it is positive or negative, over the velocity of the wave, which is, in this case, the velocity of the sound. However, if our source is actually moving, you notice that it is catching up with the wave fronts it's producing. So the wave fronts are compacting in front of the source. Notice them here. But then they are spreading apart behind it. So an observer up front is going to see a higher frequency. An observer on the back is going to see a lower frequency. Again, an observer up front is going to see more frequent wave fronts. An observer on the back is going to see the wave fronts less frequently. So in summary, when the source is coming towards you, so for example, if we have the observer here and the source is coming towards you, the distance between the waves or wave fronts decreases, resulting in a higher frequency. However, when the source is moving away from you, that's when you are here, and the source is moving away from you. That's not exactly what we have seen in the animation, but it's the same idea again. The distance between the waves increases, the waves or wave fronts increases, making the frequency decrease. Mathematically, that's expressed this way. This is the frequency as measured by the observer. This is the original frequency as produced by the source. Now, it is the original frequency over, it's not multiplied like last time, over 1 minus the velocity of the source over the velocity of the wave. Again, the wave in this case is sound, so that's the velocity of sound. One might ask, what happens when both move? When both the source and the observer move? We just combine the equations. So the frequency as detected by the observer is the frequency as produced by the source times what we had in the numerator when the observer was moving, so 1 minus VO over VW over 1 minus Vs over Vw. Remember, Vw is the velocity of the wave, which is in this case the velocity of sound. Vs is the velocity of the source, and Vo is the velocity of the observer. Also remember the signs. Velocity of the observer, so when we talked about the source, we had the source here, but the observer moving away, that's when it was positive. For the velocity of the source, the observer was here, the velocity of the source was moving towards him, that's when it was positive.